All right, hello applied students. Welcome to this video on writing exponential equations. So we are going to start by creating an exponential equation for a given scenario. So let's pretend we are going to deposit $1,000 into the bank. And the bank tells us that each year we will earn 3% interest. That's really, really generous. But let's pretend for a second that we're going to earn 3% interest. So we're going to start. Let's make an XY table to explain what is going on in this situation so we can identify what's happening. So we're going to have T, which will be time in years for us, and we'll have B of T. M of T, which will be our money, the amount of money that we have. So we're going to start at year 0, and in that year we will have exactly $1,000. After 1 year, here's what the bank promises to us. They tell us that we will earn 3% interest. So that means we need to figure out what 3% of our money is. So we turned 3% into the decimal form. This is 3% as a decimal, to figure out what 3% is. So if I type that into my calculator, 1,000 times 0.03, that is equal to 30. Wait, I'm not gonna have $30 in my bank. That's what I earn on top of the money that I already had. So I also get to keep the $1,000 that I had from before. So now in my bank account, I have $1,030. Okay, let's do one more in this drawn out fashion and then I will shorten my idea. So now if I do it again and I try to figure out what is 1,030 and I want to know what 3% of that is, well, let's type in 1,030 times 0.03. That is $30.9. And that is going to be on top of the $130 that we already had. So now I'll have $1,060.90. So if you noticed, I was writing in this secret times 1 over here on the side for both of these situations because I had to think about the $1,000 that I already had that I'm adding to. So if we notice in this situation, we have 1,000 times 0.3 and 1,000 times 1. Instead, I could think of this as 1,000 times 1.03. I'm distributing out the 1,000 from these two situations. Let me back up a little bit further. If I distribute this out, I would end up with 1,000 times 0.303 plus 1 because of this 0.03 and that 1. Or 1,000 times 1.03. And the way that I want us to read this and think about this that I'm talking about right here is let's take the $1,000 that I already had, $1,000 that I started with. And then let's build on it. We are building on it, and it's 1.03. The 1 is equal to the 100% of the money that we already have. We're not taking away any money. The 100% of the money that we already have plus 0.03, which is the interest, that 3% interest. So now I can keep going in this way, and then every time, instead of doing this in 2 steps, I can just multiply by 1.03, sorry, every single time to get my next 3 numbers. So let me do those out really quickly. So if I do 1,060.9 times 1.03, I get 1,092.73 for year 3. After 4 years, I would have $1,125.51. And finally, after 5 years, I would have $1,159.27. So this is great, and this can tell us 5 years, but what if I asked a question about like the amount of money that you would be able to donate to your great-great-grandchild? So I wanted to know when T was, I don't know, let's say like 90. I wanted to know 90 years in the future, something that you're going to give to your grandchildren, your great-grandchildren, way, way down the line. I don't want to have to continue this process of multiplying and continuing and finding all of the numbers in between. I would love to be able to have an equation where I could just plug in the value of 90 that I know and get to my answer more quickly. So what we're doing on our y values every time, in our y values right now, we are multiplying by 1.03 every time. So in order to do 90 years, what I would do is I would start at 1,000 and I would multiply by 1.03 times 1.03 all the way out forever and ever so that I have exactly 90 of them. In the end, I would want 90 of these guys. 90 times to equal what's going on in this situation. But guess what? We have a wonderful way in math that we can shorten this idea of repeated multiplication. If I'm multiplying a number by itself over and over and over again, I'm essentially doing a number to a power or an exponent. This is the same as saying 1.03 raised to the 90th power, which says take that 1.03, multiply it by itself 90 times. And then multiply that by the 1,000 that we started with. That is essentially what we've been doing each of these times, but written out more generically. And since that t in this case was 90, that's why that corresponds with the 90 that is here, which also tells me that I can generalize this situation and think about some m of t equation, which would be starting with our $1,000 that I know that I have, multiplying by 1.03 however many times for however many years I want into the future. Now, like we did for our money problem, this was one that was growing. So we had a number that was larger than 1 inside. The thing that we will know for sure, and a fact that we get to know, is when we have an exponential function like this, it will look like some a times b raised to the t. Let's call this the generic form, generic exponential. If this is my generic exponential, here's the things that I know. If b is greater than 1, my function is going to grow. If b is less than 1, my function is going to shrink. The mathematical word we use for that shrinking is decay. So we have some kind of growth or decay that can happen. So I want to consider a situation of decay really quickly, which will be more similar to what we're talking about for amoxicillin. That will be in our next video. If you'd like to look at the decay one, go to the next video just so I don't make this one way too long for you all, for YouTube purposes and things of that nature.